In this video, we are going to use the definition of series convergence to expand upon our ability to show that different series converge. In particular, we want to be able to develop a test for whether or not geometric series converge. So I would like to start by proving a property of convergent series. Specifically, I'm going to suppose that the series, the sum from k equals 0 to infinity of a sub k, and the sum from k equals 0 to infinity of b sub k, that those two series both converge. Then, if that is the case, I can say that the sum from k equals 0 to infinity of a sub k plus b sub k converges and is equal to the sum from k equals 0 to infinity of a sub k plus the sum from k equals 0 to infinity of b sub k. Furthermore, if c is a constant, I can also show that the sum from k equals 0 to infinity of c times a sub k is in fact c times the sum from k equals 0 to infinity of a sub k. Now what I would like to do is both use the definition of series convergence and properties that I know about finite sums to show that these properties are true. So let's look at the first property. I'm going to let a sub n be the nth partial sum of the series sum from k equals 0 to n a sub k. And then b sub n is going to be the nth partial sum for the series sum from k equals 0 to n of b sub k. Now, both the series with the sum of the a sub k's and the sum of the b sub k's converge. So I can use the definition to say that the limit as n goes to infinity of the partial sums converges to some number. I'll call that a. And we know that the sequence of partial sums b sub n must also converge if the series converges. So the limit as n goes to infinity of b sub n must also be a finite number. We'll call that number b. Now, I'm going to define the sequence of partial sums for the sum from k equals 0 to n of a sub k plus b sub k. Now my goal in defining that sequence of partial sums is to show that the limit as n goes to infinity of c sub n also converges. Well, this is a finite sum. So that means that I can use properties of finite sums to break this up into two sums. It's the sum from k equals 0 to n of a sub k plus the sum from k equals 0 to n of b sub k. So the sequence of partial sums for c sub n is actually just a sub n plus b sub n. Well then, if I want to take the limit of that sequence of partial sums of c sub n, well, that's actually just the limit of the sum of the two sequences, a sub n plus b sub n. But we know from our properties of limits that we can write that as the limit of the first sequence plus the limit of the second sequence. And each of those limits exists, and so that equals a plus b. And now we've shown that the limit of the sequence of partial sums c sub n exists. So we've now proven that property A is true. And so I'm going to say that this has been demonstrated, QED, or I'm going to put like a little square like the book does. Okay, and sometimes we call that the celebration square, the square that you get to at the end of your proof. So now that you've done this proof for our property A, I encourage you actually to prove on your own property B using the same technique, looking at the limit of a sequence of partial sums. So that's one property of convergent series that allows us to show that more different types of series converge without too much work, because we can break up our series into sums of convergent series. But now I want to talk about what are called geometric sums and geometric series. So we're going to let S sub n equal the sum from k equals 0 to n of r to the k, where r is some number. Okay, this is called a geometric sum. So I want to write out what the terms look like for the nth partial sum. So we have r to the 0, which is 1, plus r to the first, plus r squared, plus r cubed, plus r to the fourth, etc., all the way down to r to the nth power. And I want to show that the limit of the sequence of partial sums either converges or diverges to show whether the series converges or diverges. So there's a little trick to this one. I'm going to multiply my sequence of partial sums S sub n by r. So if I multiply everything by r, I'm going to get r plus r squared plus r cubed plus r to the fourth plus r to the fifth plus, going to keep going down. There will be an r to the nth term because we'll have, say, an r to the n minus 1 term before r to the n. So an r to the nth term plus r to the n plus 1. Now I'm going to take S sub n and then subtract r times S sub n. So in fact, imagine that I'm essentially putting a minus sign here, and then I'm just going to subtract these terms. Well, I'll get a 1, and then you'll notice that I'll get an r minus r, so those will cancel, an r squared minus an r squared, so those will cancel, an r cubed minus r cubed, r to the fourth minus r fourth. A lot of these terms are going to cancel. Even the r to the fifth will cancel. So will the r to the n minus 1. In fact, r to the n's will cancel. And so what I'm going to be left with is just r to the n plus 1. Okay, so Sn minus Rsn is equal to 1 minus r to the n plus 1. Well, let me rewrite that just a little bit. That says that Sn times 1 minus r is equal to 1 minus r to the n plus 1. So I can actually come up with a formula for the nth partial sum by dividing by 1 minus r, and it says the formula for the nth partial sum is 1 minus r to the n plus 1 over 1 minus r. And so now that I have a formula for the nth partial sum, I can ask the question, does the sequence of partial sums converge? Okay, so what happens if I take the limit as n goes to infinity of S sub n? Well, that limit is going to be 1 over 1 minus r if the absolute value of r is less than 1. So if we raise r, say, to the n plus first power, well, that sequence is going to get smaller if r is less than 1 in absolute value. And so as I raise it to the n plus first power and I let n get larger and larger, this sequence is going to go to 0. And so that would leave me with 1 over 1 minus r. Now, if r equals 1, then this is not well defined. And then if r is bigger than 1, then it'll go off to infinity. So let's do one example with these geometric sums. So we've heard before that repeating decimals can be expressed as fractions. So I want to express 0.23, 23, 23, 23, etc. as a fraction. Well, that's actually 0.23 plus 0.0023 plus 0.000023 plus 0.00000023, etc. And I can express those as fractions. That's 23 over 100 plus 23 over 10,000 plus 23 over 1,000,000, etc. Now, I'm going to note that 10,000 is actually 100 squared. And 1,000,000 is actually 100 cubed. And so I can start to see a pattern. In fact, this looks like the sum from k equals 1 to infinity of 23 over 100 to the kth power. And so now I'm starting to see that this is looking like a geometric sum. I'm going to factor out a 23 over 100 in this case, so that this actually becomes the sum from k equals 1 to infinity of 1 over 100 to the k minus 1. It almost looks like my geometric sum. I don't have r to the k power, I have r to the k minus 1 power. So I'm going to let n be k minus 1, so that then this becomes 23 over 100 times the sum from n equals 0 to infinity of 1 over 100 to the nth power. And now I see my geometric sum starting at the index 0 and going to infinity. Now 1 over 100 is actually equal, or it's, sorry, 1 over 100 is less than 1. So I can use my formula for geometric series. So this is actually going to be 23 over 100 times 1 over 1 minus, and then the r is 1 over 100, which is clearly less than 1. Okay, well, that's going to be 23 over 100 times 1 minus 100 is 99 over 100, and 1 over that is 100 over 99. So this is actually 23 over 99. And 23 over 99 is the fraction that represents 0.23232323. And you can check that just by using your calculator.